This animation shows a physical water tank filling up under pressure, right next to a parallel plate capacitor charging from a battery. These systems share the same logic. In the electrical circuit, the physical size of the tank represents your capacitance, and the water pressure pushing into it represents your voltage. To find exactly how much electrostatic energy is stored, we use this standard equation, U equals 1/2 CV squared. Because the voltage term is squared, the pressure applied has a disproportionate effect on the total energy compared to the capacitance of the plates. Let's apply this to a baseline calculation. We have a 12 picofarad capacitor connected to a 50-volt battery. We'll pull our variables, C and V, out of the text and into a working column. Before we drop these numbers into our equation, we have to handle the prefix. Pico means 10 to the negative 12th power. We need to explicitly expand that out when substituting our values, so our 12 picofarads becomes 12 times 10 to the negative 12. Next is the order of operations. We must square the 50 volts first, which gives us 2500, before doing any other multiplication across the line. Multiplying 1/2 by 12 times 10 to the negative 12 and then by 2500 yields 15 times 10 to the negative 9th joules. We can collapse that negative 9th power into the nano prefix, giving us a final stored energy of exactly 15 nanojoules. So long as you correctly convert your scientific prefixes and strictly adhere to the order of operations, calculating baseline energy is a very predictable process. This schematic shows our starting point for a slightly more complex multi-stage scenario, a 600 picofarad capacitor charged to 200 volts. Soon, we are going to disconnect it and wire it to a second entirely empty 600 picofarad capacitor. Our final goal is to determine how much energy is lost during that transition. But to measure a loss, we must calculate the energy in this initial state. 1/2 times 600 times 10 to the negative 12 times 200 squared. This resolves to 12 times 10 to the negative 6 joules, or 12 microjoules. Taking the time to establish a definitive baseline measurement like this is a mandatory step before you try to analyze any dynamic physical changes in a circuit. Let's look at the actual connection event. When you connect a charged capacitor to an identical empty one, the electrical charge flows between them, spreading out evenly until they reach equilibrium. This physical spread alters our variables because the total charge is now shared across a larger system. Since the capacitors are identical and the total capacitance has doubled to 1200 picofarads, the potential difference across the whole system drops to exactly 100 volts to keep the shared charge in balance. Now it's your turn. Pause the video here. Take these mu state 2 variables, plug them into the core formula to find the final energy, and subtract that from our initial 12 microjoules to find the total loss. Tracking how variables shift in a closed system allows for a complete analysis of multi-stage circuits. Let's check your work. We take our new system capacitance of 1200 picofarads and our new equilibrium voltage of 100 volts and substitute them right into our formula. Square the 100 to get 10,000, multiply across, and we land at a final total energy of 6 microjoules remaining in the system. We started with 12 microjoules, we ended with 6. Subtracting the final state from the initial state confirms that exactly 6 microjoules of electrostatic energy were lost during the connection. The math shows a drop in energy, but it's important to understand the physical reality here. No electrical charge actually vanished. Instead, half of the total stored energy was simply dissipated into the environment as heat, or a tiny spark, at the exact moment those wires touched. This cheat sheet graphic highlights the 2 most common math errors to watch out for: carefully translating your scientific prefixes, and always remembering to square your voltage before multiplying across the equation. We can also add the situational rule we just proved. When you connect 2 identical capacitors, the charge spreads perfectly evenly. You double the capacitance, and you have the voltage. Nailing these core algebraic steps builds the foundation you need to confidently analyze dynamic electrical systems in the real world.